So let's just say that today's episode was difficult to make. We're going to be talking about quantum field theory today. And quantum field theory is at once our deepest and most profound understanding of the nature of the universe, and an extremely conceptually difficult subject filled with lots of abstract mathematics. It's also notoriously the most difficult subject that a theoretical physics graduate student will have to take. Describing a theory like this in an understandable podcast episode might be a silly thing to even attempt, but we love our listeners, and there's no way to appreciate the success and depth of our physical theories without talking about quantum field theory. So, in today's episode, what is quantum field theory, and what does it reveal about the innermost workings of our universe?
This episode of Why This Universe is supported by Wondrium. Wondrium is a mind-blowing subscription service that offers thousands of video and audio courses on a huge range of topics. I've been a big fan and a regular consumer of Wondrium's content for the past 15 years or so, and over that time I've listened to dozens of their courses, including ones on history, philosophy, literature, math, and even science. For me, it's like taking an intro-level university course from a great professor on a subject you've always wanted to know more about, but without the big tuition fee, and all in the comfort of your own home or daily commute. Recently, I've started to listen to a series of lectures on Wondrium on the topic of Norse mythology. Over 24 lectures, this course explores how the people of the Norse culture view things like fate, as well as their place and significance in their world. Along with these more heavy questions, these lectures also contain a lot of fun stories about things like gods, dwarves, spells, and berserkers. It was a blast to listen to. So if you want to learn more about Norse mythology, or really just about anything else, you should give Wondrium a try. You can sign up for Wondrium now through our special URL to get a free month of unlimited access. Just go to wondrium.com/universe. That's wondrium.com/universe.
You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago.
To understand how and why physicists developed quantum field theory, let's back up and talk about what came before, quantum mechanics. Yes, quantum field theory and quantum mechanics are very related, but ultimately different sorts of theories. And it turns out that quantum field theory developed because of a certain failure of quantum mechanics.
The earliest ideas behind quantum mechanics go back to 1905, when Einstein proposed that light isn't only a wave, but also comes in discrete quanta, or particles that we today call photons. A few years later, in 1913, Niels Bohr expanded on this idea, showing that if you treated electrons not only as particles but also as waves, you could explain and understand the workings of hydrogen atoms as well. These ideas, both Einstein's, Bohr's, and others, all kind of pointed us to this conclusion that the stuff that we find in our universe has some particle-like features and some wave-like features kind of all wrapped together at the same time. We call this particle-wave duality. And in the 1920s, this program of investigation really flourished, growing into this thing that we now call quantum mechanics. So before I tell you where quantum mechanics fails, I want to emphasize that it's really a wonderful and a powerful theory. But like other great theories, of course, it has its limitations. Most importantly, quantum mechanics treats space and time the way that like Isaac Newton would have thought about it. Okay, just kind of the static backdrop that things move through. But Einstein, by this point, had already taught us that space and time aren't at all Newtonian. They're different. They're relativistic. But just like you can safely use Newton's equations to calculate a lot of things, trajectories of cannonballs or motion of balls on a pool table or whatever, you can use the equations of quantum mechanics pretty reliably as long as all of the things that you're trying to consider are moving at speeds way slower than the speed of light.
So physicists needed a new theory to help them explain the quantum behavior of particles that move relativistically, or near the speed of light. And this theory of relativistic quantum mechanics is what came to be known as quantum field theory.
All right, so what goes wrong if we try to use quantum mechanics to describe particles that are moving at speeds close to the speed of light? Well, according to relativity, the order that different events take place in can depend on the frame of reference that you're observing those events from. So, like, let's say, for example, I pick up my phone and I call you, Shalma, and you pick up then as your phone rings and you say, hello. In some other frame of reference, you might worry that Shalma picks up her phone first and says hello, and then I dial Shalma's number to call you. And that obviously doesn't make any sense. This is something that violates causality, and any theory that works like that is just nonsense. It has to be a broken theory. That can't be the right answer. And Einstein knew about this. He knew that causality couldn't be violated. And there was a solution to this built into his theory of relativity. And that solution is that the speed of light is the speed limit for all things in nature. Nothing can move faster than light. So as it turns out, according to relativity, in every possible frame of reference, I'll make that phone call to you before you pick up and say hello. In other words, it's fundamentally a causal theory. Relativity's speed limit on equal to the speed of light is what ensures that that will be the case. In the context of quantum mechanics, though, the problem of causality comes up in a new way. So if you've heard about quantum mechanics before, you've probably heard about something called the Heisenberg uncertainty principle, which says that the more you know about the location of something, the less you could possibly ever know about the velocity of that thing. This means that if you know exactly where two events took place, you can't know anything at all about how fast these things might be moving after that measurement occurs. That makes it possible that an event could cause another event in one frame of reference, while that second event might take place before the first event in another frame of reference, causing all sorts of causal havoc and utter nonsense to ensue. So in other words, quantum mechanics just doesn't seem to be compatible with Einstein's theory of relativity. So how do we solve this? Well, if we consider a frame of reference where event A is seen to cause event B, we could imagine this might take place by an electron traveling from where event A took place to where event B is taking place. And then we ask, what would this look like in that other frame of reference where the events are happening in the opposite order? Well, that electron, which was moving through space to that other observer in that other frame of reference, will look like an electron-like particle with a positive charge moving backwards through time. So let me repeat that. To one observer, you have an electron moving forward in time. To another observer in a different frame of reference, what they see is a positively charged electron-like thing moving backwards through time. It turns out that this positively charged thing is what we call a positron, an antimatter counterpart to the electron. And it's the existence of this antimatter that makes it possible to reconcile quantum mechanics with the causal nature of relativity. In other words, in order to make quantum theory causal and not have these sorts of logical problems, quantum field theory says you don't need just matter, but you need antimatter counterparts for all of the kinds of particles that exist in nature. All right, so this is a big deal, so let me stop and try to explain it one more time. If you take the theory of quantum mechanics and try to make it consistent with relativity, you find that causality breaks down. You get utter nonsense. To resolve this and to make the quantum nature of our universe consistent with relativity, we have to interpret particles that are traveling backwards in time as particles of antimatter, antiparticles. These antiparticles have exactly the same amounts of mass as their particle counterparts, but opposite amounts of electric charge and other kinds of quantum charges. To incorporate antimatter into our quantum theory, we're going to have to go beyond quantum mechanics into something we will call quantum field theory. One of the limitations of quantum mechanics is it doesn't allow for particles to be created or destroyed. It doesn't really allow the number of particles in a given system to ever change. Electrons, for example, can move around and gain or lose energy in quantum mechanics, but they can't ever disappear or come into existence. At speeds much below the speed of light, this is actually how electrons behave, so quantum mechanics works just fine in those circumstances. But at high speeds or high energies, you can and do, in fact, create and destroy these kinds of particles all the time. as long as you create or destroy along with them an equal amount of antimatter. Connecting this to our earlier argument about causality, we know that quantum mechanics is doomed to predict nonsense unless, that is, you can also create or destroy particles in the process. This is kind of a loophole that allows quantum field theory to succeed where quantum mechanics failed. The first elements of quantum field theory were introduced in 1927 by Paul Dirac. Before Dirac, quantum mechanics was carried out by using something called the Schrodinger Equation. This equation could be used to calculate how a wave function associated with an object could behave or evolve. And this wave function, in turn, could be used to calculate the probability that an object in question might be found at a given location or with a given speed or energy and so on. This approach worked pretty well for slow-moving electrons, but it didn't work to describe photons that made up the electromagnetic field. After all, photons travel at the speed of light, and Schrodinger's equation is fundamentally an equation for slowly moving objects. To understand photons and the electromagnetic field, Dirac needed a new theory. Dirac's theory of quantum electrodynamics, which is just a fancy way of saying a theory of electrons and photons, could be used to calculate and explain a variety of phenomena that the Schrodinger equation could not explain. For example, it could be used to describe how an electron moving from a high energy state into a lower energy state could lead to the creation of a photon. In quantum mechanics, you couldn't have a new photon just come into existence, but nature does this all the time. To understand how this could happen, you couldn't rely on quantum mechanics. You needed quantum field theory, or in this case specifically, you needed quantum electrodynamics. Dirac's approach to the quantum world made a variety of other correct predictions as well, including the details of the light that was emitted from hydrogen atoms. Dirac recognized many of the implications of quantum field theory pretty early on, and certainly before anyone else seems to have. Among other things from the mathematical structure of his theory, Dirac was the first to make the bold prediction that antimatter must in fact exist. And incredibly, it's only just a few years later that the positron was actually observed for the first time in cosmic ray experiments carried out by Carl Anderson, 1932. The next big step toward a more modern version of quantum field theory took place in 1933, when Enrico Fermi came up with his theory of beta decay. Beta decay is a process by which a neutron disappears and becomes replaced by a proton, an electron, and an antineutrino. This was the first theory to contain what we would now call the weak nuclear force, which is, of course, a central part of the standard model of particle physics. And importantly, the creation and destruction of particles was a central element in Fermi's theory. As a side note, I'll mention that Fermi's original paper on beta decay was rejected by the journal Nature when he submitted it to them. They said it, quote, contains speculations too remote from reality to be of interest to the reader. I like to tell this story to any of my colleagues who get a disappointing referee report. I find it to be a bit morale boosting.
So now we know that physicists developed quantum field theory out of the need to create a relativistic theory of quantum mechanics. But what really is quantum field theory? We haven't yet talked about all these deep truths that it apparently reveals about the universe.
First of all, in quantum mechanics, particles and other objects are described by a wave function. And this tells you where the probability of finding a particle at a given location or with a given velocity if you measure it. In quantum field theory, the picture is a little different. Instead of thinking in terms of a wave function, you can think of every particle and every wave as an excitation of a quantum field that extends throughout all space and all time throughout the entire universe. So there's one quantum field everywhere, say an electron quantum field, and where you actually find a particle that we'd call an electron is where that field is in an excited state. Among other things, this implies that any two particles of the same kind, like any two electrons, will be absolutely and perfectly identical. And the identical nature of these particles is deeper and maybe more far-reaching than you might at first think. It's more than them just being alike or being clones or something. I like to think about it like this. There's really only one, and there's only ever been one electron in our universe. That electron just exists in many places and times at once.
So quantum field theory tells us what's fundamental isn't necessarily a particle like an electron, but an electron field that extends everywhere in space. The electron that we are familiar with emerges as a particle by an excitation of this electron field. As an imperfect analogy, you can imagine that you and a friend are holding a jump rope tight, and one of you excites it by sending a pulse through, which kind of acts like a particle. Except that in the case of the electron field, there's only one kind of pulse that you can possibly create with your jump rope. So every jump rope with a pulse would have an identical pulse. And rather than there just being one jump rope, you can imagine infinite jump ropes at every point in space where each jump rope either does or doesn't have a pulse in it, corresponding to an electron or not an electron. Yes, it's confusing. And it's not just electrons, but every fundamental particle has a corresponding field. And all of these fields coexist in space, making empty space not really so empty.
In our everyday experience, there are no examples of truly identical objects. Two cars or two pencils or two people might be like remarkably similar, but there are always small differences that differentiate them. But any two electrons really are truly identical, like all the way down. This is because they're two different excitations of the same underlying electron field. In other words, they're two manifestations of the same electron, if you will. It kind of reminds me of Plato's theory of forms, if you've ever read that sort of thing. In that, and in the Republic and other places, Plato talks about the kinds of objects that you might find in the physical world, like tables or rocks or something. And he contrasts this with idealized objects like numbers or abstract geometrical shapes or something, which only exist in the realm of ideas. He says that like two tables will never be exactly alike, but every instance of the number 7 you ever encounter is exactly the same. There aren't two similar versions of 7. 7 is always 7. In this sense, in kind of a weird way, electrons and other excitations of a quantum field are more like Plato's idealized objects of ideas than they're like tables or rocks or anything. All right, so how do we know that any two electrons in our universe are exactly identical? Well, one way that this fact comes into play is through the statistics of quantum physics. So to understand what I'm talking about, let's consider an example that our common sense can kind of handle. So imagine I have 2 coins, and I'm going to flip these 2 coins, and I want to know what the odds that I get heads both times are. The answer is 1 in 4. After all, there's only one way to get heads, and there are 4 possible ways they could come up, 4 possible configurations: heads, tails, heads, or tails, heads. So 1 out of 4 of those times for a 1 in 4 chance of getting both 2 heads. But this sort of problem gets weird if I try to do the same sort of calculation using quantum objects. So for example, if I have 2 electrons and I ask what are the odds that I'll find them in some random configuration, both spinning clockwise. This sounds like it should be essentially the same problem that I asked with coins, but instead of there being a 1 in 4 chance of them being both spinning clockwise, it turns out that there's a 1 in 3 chance in this case. So let me explain the reason. So with the coins, we said there were 4 possible configurations you could find them in: heads, tails, heads, and tails, heads. But this relies on the fact that the 2 coins are fundamentally distinct from one another. If there was no distinction whatsoever between the first and the second coin, then the heads, tails, and tails, heads configurations would really be the same thing. And counting them both would be double counting. It would be kind of doing the math wrong. It would be cheating. So in the case of truly identical objects, there are only 3 possible configurations you can arrive with: heads, tails, or the configuration where one is heads and the other is tails. You can't discriminate between the 2. So in the case of these 2 electrons, they can both be clockwise, they can both be counterclockwise, or you could have one of each. And that makes the 2 clockwise configuration a 1 in 3 chance rather than the 1 in 4 that your pre-quantum intuition might have led you to guess. You might try to object to this kind of this line of reasoning by saying that you could somehow keep an eye on the two electrons in an experiment and keep track of which one's which. But by observing an electron or any other quantum particle, you're fundamentally affecting it. You're changing it and altering the experiment in the process. And also, quantum particles aren't really in one place at one time. So even talking about which of the two particles is A and which one's B, that doesn't really make sense. They could be moving back and forth between each other or something in a way that makes those sort of questions moot. So you really do have just the three possibilities. Either they're both doing the same thing clockwise, they're both doing the same thing counterclockwise, or they're doing different things. So let's take a step back and try to put everything we've talked about in this episode into context. Quantum mechanics is a great theory. It does a lot of stuff really well. We still teach it and we still use it. But it's fundamentally incompatible with relativity. When you try to build a version of quantum mechanics that can be combined with relativity without leading to violations of causality, you end up building something that we call quantum field theory. And what is quantum field theory like? Well, first of all, unlike in quantum mechanics, it has to be possible for particles in quantum field theory to be created or destroyed. Like an electron and a positron, for example, can both come into contact, disappear, and be replaced by two photons or two particles of light. Or the reverse, where you have two photons of light coming in, they interact and disappear, creating in their place an electron along with a positron. And second, particles in quantum field theory are an excitation of a quantum field that extends everywhere and at all times throughout the universe. This means that all particles of the same kind, like electrons, for example, are really just examples of the same single particle. You shouldn't think of quantum field theory as a singular theory, but rather as a type or class of theories. The standard model of particle physics, for example, is one example of a quantum field theory which has been tested rigorously with incredible precision over the last half of a century. Someday the standard model will be replaced or maybe expanded by some new quantum field theory, which includes other kinds of particles that we haven't discovered yet. And we don't know exactly what that theory will look like. It still seems likely to me that all the elements of quantum field theory we've talked about in this episode will probably apply to that new theory as well. And last, whenever we've talked about relativity in this episode, we've really just been talking about Einstein's theory of special relativity, the version that he introduced in 1905. But this version of the theory doesn't include or make any reference to the force of gravity. To understand gravity, we instead have to use Einstein's later general theory of relativity. But general relativity is not a quantum theory, and we really don't know how general relativity works with quantum field theory, whether it's a standard model or any other kind of quantum field theory. Someday we hope to have a quantum theory that incorporates gravity, what we'd call a theory of quantum gravity. Maybe this will look like something like string theory or loop quantum gravity or something like that. Or maybe it will look completely different. I think it's a totally open question for the time being. But in any case, the problem in quantum gravity is probably the biggest outstanding question in all of physics today. And it really just boils down to how do you take Einstein's full version of his theory, including gravity, and make sense of that theory, knowing what we know about the quantum world.
Today's episode was produced and edited by me, Shalma Wegsman. My co-host is Dan Hooper, a professor of astrophysics at the University of Chicago and Fermilab. Dan is also an author and has written many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. Thank you for all your support and for listening to our show. If you want to support us even more, you can subscribe to our Patreon, where you can ask us questions for exclusive Ask Us Anything episodes, as well as get the ad-free versions of our regular episodes. You can find our Patreon at patreon.com/whythisuniverse.